Let's consider a example where the random variable is the gap between the arrival of cars. Could be anything that is in this kind of a process here. And we're going to let the data be a small data set here. 1.2, 3.0, 6.3, 10.1, and 4.4 seconds, that inter-arrival time. And we're going to assume that we have Poisson arrivals which is going to tell us, if so, that from a theoretical kind of standpoint, that x has an exponential distribution, right? So our underlying probability distribution, we believe, would be fx of x, the PDF, is equal to lambda e to the minus lambda x. X is greater than or equal to 0, and of course then the question becomes, what should lambda be? Right, and the method of moments is going to give us one approach to coming up with that one single parameter. So, and part of the notation that we're going to work with here is the idea that our probability distribution is now conditional upon knowing a parameter. However, that parameter, and that just this general notation that we're going to have here, is theta for that parameter. We have one unknown parameter. And one approach that we might use in this particular case is to set our theoretical mean equal to the sample mean. And you're going to see in the method of moments that that's a typical kind of thing. That will be setting some sort of theoretical measure equal to some sort of sample measure, and in this case it's going to be the moments that we're yet to really define. Here we only have one observed parameter, so we'll only do this once, right? And for this continuous then situation here, our theoretical mean, u equal to x times its distribution, in this case given the parameters theta, right? And we're going to set that equal to 1 over n times the summation of n. And what we're going to get out of this then is a function of theta, and that's our whole goal, solve for theta. Again, theta is our general term here. What we're actually going to get in this specific case is lambda. And so our expected value of x here, when we integrate this, right, for our exponential case, we already know because we've done this work before. And if you pull out your table of common distributions, that our mean theoretically is 1 over lambda. And we're going to set that equal to our observed mean, our sample mean, right? And that was at 1 over n, which turns out to be, we have 5 of them, and the sum of the x values turns out to be exactly equal to 25. So we'll have then that equaling to 5 seconds, and therefore lambda in our point estimate approach is 0.2 inter-arrivals per second is our lambda rate. So that's our first example, one parameter kind of example of how we might use the method of moments to come up with our parameter estimation. So okay, production team, I just realized that I wrote off of the page. So what I'm hoping you'll be able to do, rather than starting all over, is to cut out the part where I finished right here, and then when I go down, also clear my throat here a little bit. And so let's slide that up, and I'll pretend that I haven't mentioned this yet, and we'll go back to this little piece so you can cut that in. So pause so you can understand where we're at. And so 1 over lambda is set equal to the observed, and therefore lambda is equal to 0.2 per second. Right? Let's look at generalizing this a little bit. Let's generalize this from one parameter to multiple parameters, and we'll illustrate it with the gamma function, which we've seen come up in the continuous random variable section for how long until the kth success. So the exponential is really just an example of the gamma distribution to the first success. Right? And the gamma function then is a two-parameter model, r and lambda. Sometimes this is a k, and that equals lambda raised to the r, x raised to the r minus 1, e to the minus lambda x over r minus 1 factorial, and x is greater than or equal to 0. So a two-parameter model, that's what we're going to illustrate this more generalized approach with. Right, so now before we had our distribution that was conditioned on one parameter, now it might be a distribution that has n parameters. We've got an illustration here where n is equal to 2. And certainly one of the first things we'll do is we'll set the theoretical mean equal to the sample mean. We did that with the previous one. And then we'll look at setting the expected value of x squared. So before, the first one was expected value of x to the first power. Now we're going to go to the x squared, and we're going to set that equal to the observed. One over n of all the squared values, sum of all the squared values of the xi, and take the average of those. Right. And we can do that, of course, again. Take the next one, So that's raised to the third power, and we'll take, again, sort of the average of all of the cubed values of our data set, so on and so forth, up to the nth product. Take the average of all of those, right? And that notion that these are moments comes from that idea. Let's look at the some sort of generic distribution here, and here's a specific x value, and that in a sense, and this is, we're plotting the distribution here, that when we theoretically are evaluating something like this, we're taking the nth moment of our probability distribution, where this could be a vector of parameters now, unknown. Right, so that's where the idea that these are moments comes from. Right, and what we're going to end up with in our n simultaneous equations, from which we can solve for the parameters. Okay, so let's go back to the gamma distribution and our specific case here, that then we have the expected value of x for the gamma is equal to r over lambda, and we'll set that equal to our observed value of the sample mean, which was equal to 5.0. That gives us one equation. Unfortunately, of course, we have two parameters, so two unknowns. We need one more. So let's look at then expected value of x squared. Right, now remember, that is also equal to mu squared plus the variance. Right, we got that really from what was the variance equal to? It was equal to the expected value of x squared minus the square of the mean. And for the gamma distribution, of course, we already know the mean is r over lambda. That's squared. And then we know for the variance for a gamma variable that that's equal to r over lambda squared. And we're going to set that equal then to the observed value of the average. Sorry, it's really critical how you do this, because you can get this all messed up. The observed value of the average of the x squared quantities, which in this case is equal to, well, we can go 1 over n sum of the square of the individual values, right? And for kicks, let's go back and actually take that glare out of there a little bit. That's not helping any. Alright, production team, I gave you another thing to have to cut out. Until I figure this out. I'm not happy about that. I'm not happy about it. You looked and looked and looked. You don't have any reason to not trust what you have. Okay, production team, we're going to redo that whole last page there. I was coughing and all the rest of it and fumbled around with my calculator, so we'll redo that. So let's go back to this gamma function then and apply it to our travel or our inter-arrival time of cars. First one here is to set the theoretical mean, which for our gamma function is going to be k over, or rather r over lambda, set equal to our sample mean equals then 5.0. But we have two parameters, so we need another equation. So let's go look at expected value of x squared, and remember that's also equal to mu squared plus our variance. Right, so theoretically here, mu squared, well, we've got our expected value, that's r over lambda squared plus the theoretical variance in terms of the parameter of a gamma variable will be r over lambda squared, and we're going to set that equal to our average value of the sum of our x squareds, and here that'd be 1 over 5, and then we take each of the individual values of x that we observed, square them, sum them up. That turns out to be 171.5, and that then is 34.3 or 34.2, 34.3. Right, so now we have two equations and one unknown. Right, we know that r over lambda is equal to 5, so square it, that's 25. Plus, and then we can multiply by r, divide by r over here, and we'll get then 25 over r, and that's equal to 34.3, and so r is equal to 25 divided by 9.3, and that's equal to 2.69-ish, from which then we can find out that k lambda is equal to r over 5, and our lambda is equal to 0.54. And so that's another way of using the method moments here for the gamma function. Right? Now, oftentimes when you're using this approach, you're only depending on one parameter, but you can certainly broaden it on out. Let's do one more example here with the uniform distribution. Mostly because it's such a nice, easy, simple one to use. And remember, the uniform distribution will do a continuous random variable here. So called because it, of course, has a uniform value up to a upper bound. Let's let theta be our upper upper bound. Right? And once again, we've got, in this case it's from 0 to the upper bound. We're going to set that theoretical mean, which will be theta divided by 2, and we set it equal to our observed sample mean of 5, and that means that theta would equal 10 from the method of moments perspective. It's the max value here. That's theoretically going to be allowed, that preserves the sample mean. The problem is the actual max value that we have in our data set was equal to 10.1. So this approach actually didn't do very good out here for the extreme values, and that's a critical thing, that the method of moments approach is not very good in the tails because it emphasizes the body of the distribution, the body of the data. So if that's where you want to model, then maybe that's okay, but if you're interested in extreme values, then method of moments may not be particularly great. And so we're going to talk about another approach that takes a slightly different spin of all of this, and that's the maximum likelihood method.